Welcome everyone. So we are about to start this morning session on attribute-based encryption and friends. So we have 3 talks first, then there is a track switch break, and then 2 more talks. So the first talk is on fully adaptive decentralized multi-authority ABE, and Ilan Komarkowski is going to give the talk. Please.
Okay. Hi, everyone. Thanks for coming to my session. I'll talk about fully adaptive decentralized multi-authority ABE. This is based on joint work with Pratish Datta and Brent Waters. So I'll start by telling you what ABE is. ABE is just a public encryption scheme, but it is associated with a feature that allows you to generate keys for restricted, that can allow you to decrypt various ciphertexts. So it's restricted keys that can help you restrict only certain ciphertexts. Specifically, we'll talk about the ciphertext policy variant, where you can generate secret keys that are associated with a set of attributes and ciphertexts that are associated with functions. And a ciphertext will allow you to decrypt a secret key will allow you to decrypt a given ciphertext only if the function on the set of attributes is satisfied. And if it's not, it should be like in a standard public encryption scheme where you don't know any key. Okay, so this is attribute-based encryption. We'll be talking about further generalization of ABE that's motivated by the following deficiency of standard ABE. So if you remember standard ABE, there's one authority or one entity that's in charge of generating secret keys. This is the entity or organization that decides who gets a key for having some attribute and who doesn't get the key for having the same attribute. But this is not necessarily the case when you want to use ABE in a larger context. For example, if you have a huge system that includes many different authorities, it doesn't really make sense that one authority will be in charge of generating all secret keys. So imagine, for instance, you have a really large system where you have large organizations involved, like the DMV, the military, maybe some university, and each organization should be in charge of generating their own keys. Right? The DMV is the one telling people whether they have a driving license or not. And the university is the one issuing PhD certificates, and so on. And this is what multi-authority ABE comes to solve. This is an idea that was put forward by Chase about 15 years ago and has received quite a lot of attention since then. What do we expect from an MAAB, or what we think is the right definition of MAAB or multi-authority ABE? The system is set up, and at that point, anybody can just join the system. I want to be an authority that generates tokens for being my friend. Or some university can join, like a new university can join and say, okay, I'm issuing new PhD certificates. So authorities should be able to join the system without knowing who else is in the system, without ever talking to them, without even knowing that they exist. There should be no bound on the number of authorities. All of the authorities, like anybody can join at any point in time. It doesn't matter who joined earlier and who joined later. And whenever an authority joins the system, it should also be able to generate keys for attributes that it possesses without ever talking to anybody else. So it's completely distributed, almost no coordination between the authorities, except perhaps some global parameters that are set up at the beginning of the system, at the start. Okay, so this is what we imagine a real multi-authority ABE system to look like, and these are the features that it should possess. So here's a concrete example. Imagine these 3 gentlemen, each having some attributes. So for example, the first guy has a key for having a driving license. The second guy has a key for having a PhD, and the third guy has a key for being a veteran and having a PhD. And now imagine this lady generating 2 ciphertexts. One says hi, the other says bye, but the first one is with respect to the conjunction of PhD and driving license, and the second one is PhD and veteran. So if the system behaves as it should, then the third gentleman should be able to decrypt ciphertext 2 because he has 2 keys, one for having keys for 2 attributes. One is having a PhD and one is being a veteran, but nobody else should be able to decrypt ciphertext 1 because nobody has 2 keys that satisfy the relation. Okay, but now you should ask yourselves, okay, but how does the system distinguish between different people if it's completely non-interactive and I didn't ever meet anybody? So we assume the standard solution for this issue is to assume a model where parties have some identifier. We call it a GID model, a global identifier model. It's some number that's associated with each party in the system. It's something that's set up once and for all when the system set up and the user joins the system. And it's something that shouldn't be chosen by the user. It's like a number that's given to you. So just imagine something like a social security number. And this, of course, allows you to distinguish between different people, right? Okay, so this is the model. So now that we understand the motivation and the model, let me be more precise about the syntax. So the syntax first, there's a global parameter setup. So you first generate global parameters. Then authorities can join the system, generate the public key and the master secret key. Once they publish the public key and keep for themselves the master secret key, of course, then they can generate keys for parties, for specific GIDs. People can encrypt messages with respect to functions associated with a set of public keys. And if you have sufficiently many secret keys, you can also decrypt a given ciphertext. And correctness is, as in standard ABE, if the function is if the set of attributes that you own satisfies the function, you can decrypt, and if it's not, then you cannot. How do we define security for this complicated distributed primitive? So there's kind of quite a lot of definitions out there. So I'll give you first an abstract definition, and then I'll give specific details. So an abstract definition is the standard one that you see in every encryption scheme. The challenger first generates the public keys, the public parameters of the system, the global parameters. The adversary then issues a bunch of queries. Adaptively, the challenger responds to these queries. At some point, the adversary says, okay, I'm ready to generate the challenge. He chooses two messages, says, okay, encrypt one of them at random. He gets back the encryption of one of them. Then again, it issues a sequence of queries. It gets back responses. And when it's ready, it should try to guess which ciphertext was encrypted during the challenge phase. And the scheme is said to be secure if the adversary cannot win this game with more than negligible probability. So this is an abstract game. Let's see what kind of queries we can do. So there are three kinds of queries. The adversary can say, okay, I want to generate the following authority. So set up the DMV authority. It gets back the public key. The challenger keeps for himself the master secret key. The adversary could corrupt an authority. So we could say, okay, give me the master secret key of this authority, and it gets back the master secret key. And it can just say, okay, give me a secret key for a particular GID with respect to a non-corrupted authority. And it gets back the secret key with respect to the authority and the GID that it asked for. And the challenge is what you would expect, two messages and the policy. And the policy should not be trivially satisfied by the keys that the adversary holds, of course. And the challenger chooses one of the messages at random and encrypts the message with respect to the policy along with the public keys. So this is the strongest definition you can imagine. We call it fully adaptive security. It allows for all types of queries at any point in time. So this is the strongest definition you can imagine. Every sequence of adaptive queries the adversary does could be any query from set up an authority, corrupt an authority, or generate a secret key. So this is the strongest definition. A weaker definition that has been considered in the literature quite a lot is one where you have an additional phase where the adversary commits on the set of corrupted authorities at the beginning of the game, right after seeing the public parameters. He gets back the master secret keys for the corrupted authorities and also gives the public keys for the non-corrupted authorities. And from that point on, there's no point in corrupting authorities. They're all committed to, so these two kinds of queries are not allowed. So this is the adaptive security game. And there's an even weaker security definition that we call static security, where the adversary just makes all choices at one go. He chooses everything once, he gets the response, and needs to decide what happened. He needs to decide what was the challenge. Okay, so this is the weakest definition. These are the known results. I won't get into to telling you what every paper achieved in comparison to the previous papers, but I just want you to focus on the column, the security column. None of these works achieve the full adaptive security definition, and this is what we do. Our main result is the construction of a multi-authority ABE system supporting NC1 policy structures based on standard assumptions in prime order bilinear groups, and we achieve the strongest possible notion of security that we call fully adaptive. Okay, so I have about 9 minutes, so I won't have too much time to tell you what we do, but I can sort of try to convince you why this problem was open for such a long time, and why trivial things don't work, and why previous schemes inherently didn't manage to get this security notion. It's not something that they just didn't try. Okay, so the first thing you should ask yourselves, why can't you just do the standard thing like complexity leveraging or just guess the set of corrupted authorities? The answer is actually pretty easy for this question. If you do a guessing style argument, you sort of need to bound the number of corrupted authorities in the system, which also bounds the number of authorities in the system. And this is not what we would imagine from a fully decentralized multi-authority ABE system. So something trivial doesn't work. In terms of techniques, I'll try to tell you what previous works did and why they failed to achieve this security notion. So the first work that achieved the definition of multi-authority ABE, as I defined it, is by Luco and Waters from about a decade ago. And they used the dual systems framework, which was introduced just a couple of years earlier. And all follow-up works, without any exception, basically follow the ideas of Luco Waters in some way. So it's enough to focus on that scheme to see why all schemes fail to achieve the security definition. Okay, so I'll tell you in 2 words how dual systems work. The main idea in dual systems framework is to allow each component in the system to have 2 modes, a normal mode and a semi-functional mode. And the cool thing about these 2 modes is that they can be mixed and matched, so you can use normal keys with semi-functional ciphertext and vice versa. But once you try to use semi-functional keys with semi-functional ciphertext, the system fails. Okay, so this is the main idea in dual systems framework, and this structure of building your system allows you to do the following style of proof. It allows you to first take your ciphertext and change it to semi-functional. This doesn't change anything in the system because you can mix and match semi-functional keys with semi-functional ciphertext. And then you can do very small hybrids to change the keys one by one to semi-functional. And when you're done, you can just change the ciphertext to random, right? Because you cannot mix and match semi-functional keys with semi-functional ciphertexts. But in MAAB, this doesn't work. Why? Because the adversary might hold master secret keys for some authorities, and it can generate secret keys by himself. And you cannot change the secret keys that the adversary generates in his belly, right? So the MAAB setting is much more complicated, and the dual system framework, at least in the most general sense, that cannot be applied. So here's what prior works did. This is how they resolved the problem. They assumed that the adversary commits on the set of corrupted authorities at the beginning of the game. And this allowed them to sort of take all the information from the corrupted authorities and sort of route it around the proof. So they managed to somehow handle all of the corrupted authorities at one shot, information theoretically, by just changing the way the access policy is defined. And now the rest of the proof didn't need to care about corrupted authorities at all. And they just applied the dual system framework on the non-corrupted authorities, which are all the authorities that exist in the system. And so this is maybe one syntactical problem or one logical flaw in prior works. But actually there is a technical reason why their scheme could not be made adaptively secure, even if you ignore the fact that these corrupted authorities were routed around. If you look at how their scheme works, the authority keys are just scalars. It's some number that they called alpha in all of these works, and this number is used to, the randomness from this number is used to hide the payload of messages. And in a couple of more words, you take the message, you hash it, you mask it with something like EGG power S, and then you also provide secret sharings of S masked with alpha. So if you know sufficiently many keys, you know alpha, you can recover the shares, and then you can recover the message. If you don't know sufficiently many keys, the randomness from alpha will hide the shares, and you'll get security for your payload. But when you try to corrupt an authority, what does the simulator need to do? It needs to give you alpha. That's what corrupting an authority means. But giving you alpha is not something that is compatible with the dual framework, the dual systems framework. We don't have any security definition that involves scalars. All of the security definitions involve group elements or things in the exponent, and not just scalars. So there's really a technical barrier for making the existing schemes adaptively secure, handling adaptive corruptions. So we managed to solve this issue. Good. So I'll just try to summarize in the minute I have left. What we build is the first MAABE system that achieves fully adaptive security. We give schemes both in the composite order setting, the prime order setting, based on different assumptions depending on the setting. Our assumptions are standard bilinear group assumptions. And the major open problems, at least as I see them, is to get rid of the random oracle model, at least in the group-based setting. We have examples in the lattice-based setting where random oracles were not necessary. And I think an important line of work is to get concrete efficiency for multi-authority AB. The systems that we have are sort of theoretically interesting and practically not very efficient. They cannot really handle a very large number of entities or large number of authorities or attributes. So it's an interesting line of work to maybe even relax the assumptions, but get much more efficient schemes. So thank you.
So we have time for questions. So if you have a question, please come to the mic.
Thanks for the nice talk. I have a question regarding the GID you've mentioned in the slides. Does it have something to do with the security proof, or do you have to embed something into that?
So yeah, we use the random oracle. We apply a random oracle on the GID. And this is important for this. This is where we use the random oracle. We program the GID in the right way. So yeah, it's necessary for the security proof, and this is where the random oracle also plays a crucial part in our proof.
Thank you.
So maybe a question just to touch on, there we go, on the efficiency which you mentioned at the very end. Have you tried, well, let's say, implementing a proof of concept? And if so, do you have much of an idea of how well it was able to scale, just as an indicator, if nothing else? How large could you get it before it started to become unacceptably slow?
So we actually have implemented variants of this scheme. I don't have numbers off the top of my head, but you can support very small numbers, like 10 attributes or small numbers.
Yeah.
There's a polynomial somewhere inside, and it grows rather quickly. I don't have numbers.
Yeah, I mean, no worries. Just
head,
an indicator like tens or hundreds is okay. Do you remember what sort of order of magnitude the number of authorities you managed to get was?
I don't have the right answer, no.
Okay, no worries at all, but thank you.
Thanks for the question.
So I have another question related to efficiency. Can you say, more or less, what's the price to pay compared to the standard dual system methodology, and how does it compare with the solution with static security?
Okay, great question. So the right thing to compare to is the paper of Luca Waters that achieved the standard adaptive security definition. Our scheme is roughly twice more expensive. So we have sort of 2 copies of their scheme, roughly 2 copies of their scheme, and we do everything twice. But other than that, it's very close to the original scheme from 10, 12 years ago.
Thanks. Okay, so if there are no more questions, let's thank Ilan again. And we move to the next talk. So the second talk is on the optimal succinctness and efficiency of functional encryption and attribute-based encryption. This is a work by Ayush Jain, Uja Lin, and Ji Luo. And Ji is going to deliver the talk.
Thanks for the introduction. Well, the title of the talk is actually Quel est le prix du chiffrement fonctionnel? What's the price of functional encryption? And this is a joint work with Ayush and Rachel. So just jumping right into the definition, partially hiding functional encryption is a generalization that captures both functional encryption and attribute-based encryption. In such a system, you'll have an authority who sets up the system, generating the master public key and secret key. And then using the master public key, anyone can encrypt a private input Y tied to a public input X. And then for any function, the authority can generate a secret key for that function. And given the secret key for the function and the ciphertext, you can compute the function applied on the private and public and private inputs. And I want to mention that in our formulation, F and X are always provided in the clear because they are not hidden anyway. And in attribute-based encryption, X is just going to be the attribute, Y is going to be the message, and the function is computing P of X times Y. And in functional encryption, there's just no X. For security, we want to ensure that any information about Y beyond F of XY is hidden, given the secret key. And in fact, this has to hold under collusion. Given arbitrarily many secret keys, information revealed about Y is exactly the computation results. And formally, this is defined by IND-CPA security, where the adversary first gets the master public key and then can query multiple functions and receive their secret keys, and then choose one public input and two possible private inputs, gets back the ciphertext of one of them, and then continue the key queries. We require that the ciphertext of the two possible private inputs be indistinguishable if the private inputs are of the same length and their output are the same under those functions. So what do we want for PHFE? We want it to support expressive functionality. We want short keys and short ciphertext. We also want fast decryption. Actually, these goals are not disparate, but closely connected. You have to choose a correct way to express the functionality to provide the baseline of the encoding size and the decryption time. So here we aim for a RAM computation with unbounded output length, which means the output length could be as long as the computation time. And for short keys and ciphertext, I think the basic requirement is that anything is polynomial in the size that it encrypts or it encodes. So here in the poly, I have omitted all appearances of security parameter, but they're just there. And for decryption, we want the time to be polynomial in the description size as well as the RAM computation time. However, we know that polynomial efficiency is usually not very satisfactory. And what we actually want is basically as short as possible and as fast as possible. So here the ideal efficiency, the ideal size efficiency is that you have constant size keys and ciphertext that are rate 1 in the private input and constant size in the public input. So here, recall that F and X are provided for free, and the secret key and the ciphertext do not hide F or X, so they should be thought as a cryptographically binding hash of F and X, thus they can be constant size. Whereas for Y, since it's hidden, it must be encoded directly in the ciphertext, therefore the best we can hope for is rate 1. And for decryption, we want it to be as fast as the computation itself, with polynomial slowdown for each time step. And in addition, we also want adaptive security, and we want to construct such schemes from minimal assumptions. And in fact, there has been a long line of research into each of those questions, but they only achieve some of them, but not all of them. So the motivation or the questions of this work are the following. What is the best possible efficiency of PHFE? And are there trade-offs among different aspects of efficiency? And from what assumptions can we construct optimally efficient PHFE? And we provide answers to all of them. So positive results first. We actually construct a nearly optimal functional encryption for RAM from just functional encryption for circuits. So here, and a long line of previous works shows that the so-called obfuscation minimum functional encryption, which has a long qualifier, actually implies polynomially secure functional encryption for circuits. So if you combine our work with the previous works, then you get the best PHFE from any interesting FE for circuits. And here there are two little problems. The first is that the ciphertext is rate 2 in the private input. The second is that the decryption time additionally is linear in the description size of f, x, and y. And it turns out the second problem is either necessary or it contains a technical barrier. Let me elaborate. Sorry, before I elaborate, let me show some related works on FE. So the only previous work constructing FE for RAM is this ACFQ in Eurocrypt. And then there are a bunch of FE for Turing machines and a bunch of FE for circuits. And for most of the schemes, you can see that we improve from polynomial to nearly optimal efficiency. And there are two clouds of our scheme. The first one is that the work by GWZ actually is rate 1 in the private input. And it turns out that if we abandon adaptive security and long output, then we can also achieve rate 1. And the other one is about the dependency on the description size in the decryption time. And here comes our first negative result is unconditional space-time trade-offs for PHFE. It says that if you have a PHFE scheme whose secret key size is f to the a for some exponent a, and the decryption time is f to the b, then either a is greater than or equal to 1 or b is greater than or equal to 1. And the similar thing holds for x, the public input. So the ciphertext and the decryption time cannot both be sublinear in the description size of the public input. And this just tells us that component size and decryption time cannot both be sublinear in f and x. And this result actually holds for a very selective one key, one ciphertext secret key scheme or garbling. And the functionality used to prove these lower bounds are really simple, so it's a very strong one. Now we have known that for f and x, it's not possible to have both sublinear component sizes and decryption time. We ask, what about y? And what if we choose to have linear size components in exchange of optimal decryption time? It turns out that there's a connection to doubly efficient private information retrieval. So let me first define doubly efficient private information retrieval. You have a database, and you can apply a pre-processing procedure to this database to obtain a pre-processed database d tilde and a key k. And then using the key k, you can issue a query to some index. So the ciphertext should be thought as encrypting the index I. And then using the ciphertext and the pre-processed database, you can create a response which will review d sub I. So it's doubly efficient because there's client efficiency where the key size should be constant and the query time should be sublinear in the database size. And server efficiency says that the response time should be sublinear in the database size. And for security, we require that the process database and the ciphertext hides the indices of queries. And of course, the dream efficiency is that the D tilde is linear, has linear size in D, and the query time and response time are constant. And is such a DEPR known? Well, it's complicated, and I won't have time to go into this issue in this talk. So our second set of negative results or connections is that optimal decryption time implies double efficient private information retrieval. So suppose you have ciphertext that's x to the a in the public input, and decryption time is sublinear in x, or you can exchange x for y. Then you can obtain secret key DEPR whose efficiency will depend on the exponents a and b. And the same result is essentially also proven in ACFQ. And the new result in this work is that if you have schemes that have f to the a dependency in the secret key and sublinear dependency in the decryption time, then you can obtain a public key DEPR. And in addition to the FE result, we also obtain constant overhead I/O for RAM and attribute-based encryption for RAM. So basically, sub-exponentially secure functional encryption for circuits will imply sub-exponentially secure I/O for RAM with the obfuscated program being rate 2 in the program itself. And previously, this was on, so the rate 2 obfuscation was only known for circuits or Turing machines. And for ABE, directly from PHFE, we have constant size keys and ciphertexts, and the decryption time being linear in both the running time of the RAM and the description size of f and x. And we can also tweak our construction to move the dependency on f and x between the sizes and the time. And all of these results are unknown previously. And it's thus natural to ask whether we can obtain the dream efficiency for ABE, because the previous lower bound only holds for PHFE with functionality that's stronger than ABE. And it turns out the answer is no. Let me summarize where we stand now for the efficiency of partially hiding functional encryption. We know that Y-independent decryption time is morally equivalent to DEPR, and the dependency of F and X characterized by this work can be summarized in this little diagram where we have the time exponent and the size exponent. The negative result says that this square is impossible, and we achieve the area where the time exponent is at least 1. And the area where the size exponent is at least 1 but has small time exponent is barriered by DEPR. And for ABE, the dependency on F and X is also can be characterized using this diagram, where we have this triangle area that's shown to be impossible in another work of mine. And then we achieve the two extremes of this triangle, where the size is 1 and time exponent is 0, or the time is 1 and size is 0. And this other triangle area remains unknown to us. Okay, so now come to the technical part. Let me sketch the unconditional lower bound proof for you. So suppose now that the secret key size is f to the a, and the decryption time is f to the b, and a, b are smaller than 1. And I will choose such functions. So here the function is described by a very long random string r. and there's no public input. And there are two possible variants of private inputs. The first one is you have an index set I and a one-time pad W. And the second case is that you have just output Z. And the function applied to this private input is either R sub I XOR with W or just Z. Now we choose little n such that capital N to the A and capital N to the B is much smaller than little n, and n is much smaller than capital N. So that the secret key size is much smaller than the basically the running time of the machine, and then the decryption time is much smaller than the decryption size of F, which is the dominant factor here. And now the adversary will choose random index set and random one-time pad, and choose Z to be the right answer so that its queries are admissible. And the adversary will try to decrypt the challenge ciphertext with the secret key it receives and see how much of R sub I will decryption read from this R that's given random access to it. Now, let's analyze the two cases. When Y is in the form of IW, the secret key and the ciphertext contains much, much less of n bits of R sub I, which itself is n bits. Therefore, the decryption algorithm will have to read almost all of R sub I. And this can be formalized using an incompressibility argument. When Y is just Z, the secret key and the ciphertext and R contains no information about I, because I only appears in Z as R sub I XOR W, and it's one-time padded by W. Therefore, it can only read a tiny portion of Ri because it cannot guess where I is. And this will give us a high advantage gap, thus prove that the scheme cannot be secure if it has both sublinear size and sublinear time. And the second thing I want to give in this talk is the proof sketch of the technical barrier of DEPIR. Suppose the secret key is now F to the A, and the decryption time is F to the B with B less than 1. To implement a DEPIR, the simplest way is just to let the function be described by the database, and the Y, the private input, is the index that I want to query. And F of XY is just going to be D sub I. And for the DEPIR, the preprocessed database is just going to be the database itself plus the functional encryption secret key. And the key will be the functional encryption master public key. And to query, we just generate a functional encryption secret key for the index. And to respond, we just do the decryption. And I want to mention that the scheme that we obtain from this transformation is indistinguishability-based secure, and is selective, and is not output hiding, and is also not database hiding. However, we can apply generic efficiency preserving transformation to obtain the strongest version of security possible. And lastly, I want to show you the core of our PHFE, which is a new notion of garbling for RAM. You know, to achieve something, you have to first formulate the right definition, and the second step is to achieve this definition. But we won't have time to achieve it in this talk, so I'll just show you the definition. In our model of RAM, we have multiple tapes. There's input tape for F, for example, and input tape for D, where D can contain the public or private input. And there's also a working tape. The step circuit will take in the old state and the previous read, and output the new state and next read-write, and the output for this time step. And the memory operation can happen over any tape, and the new state will transfer to the old state for the next step. In our notion of laconic garbled RAM, the first step is to compress the tapes to obtain a short digest, which are of constant size. And then we apply the garbling procedure to the RAM step circuit to obtain a garbled RAM. And lastly, using the tape content together with the garbled RAM, we can compute the output of this RAM in time. That's t plus the input tape sizes times a polynomial in the RAM machine. And those digests should be reusable, and I want to mention that here security is indistinguishability-based instead of simulation-based, which is very important for nearly optimal efficiency. Okay, let me summarize with some open questions. What's next for functional encryption and attribute-based encryption? So on the concrete front, we wonder whether we can construct PHFE with optimal decryption time from or construct dream DEPIR. And also, we wonder whether we can achieve rate 1 in the private input with either adaptive security or long output. And on the more conceptual level, we wonder whether there's a tight relation between optimal decryption time and DEPIR. The thing is that we know functional encryption for circuits plus public key DEPIR implies optimal decryption time, but that only implies secret key DEPIR, as far as we know. So the question is that whether we can achieve optimal decryption time on private and public input given just secret key DEPIR. And then the next question is just pinning down the exact Pareto frontier of efficiency for functional encryption and attribute-based encryption, namely to resolve the stripe area. And with that, I'll end my talk. And I want to mention that the preceding version and the current ePrint are kind of out of date, and we'll revise them soon. Thank you.
So we have time for one quick question. Okay, if there is no question, we'll proceed to the next talk, and let's thank the speaker again. Okay, so the next paper of this session is Registered Attribute-Based Encryption. It's a work by Susan Oenberger, George Liu, Brent Waters, and David Wu. And George is going to give the talk.
Hello, I'm George Liu, and I'll be talking about our work on registered attribute-based encryption. So hopefully you guys aren't tired of hearing about the definition of attribute-based encryption, because well, you're about to hear it again. So attribute-based encryption was, introduced in 2005, and the basic idea here, right, is that you have a central authority which issues user secret keys, which have various attributes, and when an encryptor wants to generate a ciphertext, they can encode a policy, and if a user has an attribute key which satisfies that policy, they're able to read the message. But otherwise, even if you have multiple colluding users, which may have in combination the correct attributes, they should not be able to decrypt this message. Now, attribute encryption is great. There's been many works, constructing attribute-based encryption in various settings. But one sort of practical downside of attribute-based encryption is this presence of this central authority. And in particular, It's the fact that the central authority needs to keep a master secret key around, and this persistent secret, opens up a lot of sort of downsides in terms of when attribute-based encryption is actually usable. So, people are often, the central authority is like a central point of failure. So there's always a fear that either, the authority themselves is corrupt, or the master secret key at some point gets stolen, which happens many times in sort of like real-world security breaches. I guess one such example, it would be like the RSA secure ID breach. And in this case, you as a user may have like done nothing wrong. You keep your own like secret key safe, but like all of a sudden this entire system is now broken, right? So a workaround of this problem, or I guess like a solution to this problem, was this notion of registration-based encryption, where instead of having a central authority issue the key, there's instead this key curator, which takes in the public keys of individuals and sort of curates it into a master public key. And as more individuals join the system, they update the master public key. And if any user wants to send a message, they can simply just look at the master public key and use that to send messages to the user. So because this key is being sort of incrementally updated, we also allow the curator to send back some public helper decryption information. And this sort of solves the problem of this key exfiltration or like key escrow, because there is no master secret, right? The key curator, sort of in contrast to the central authority, is like completely deterministic and has keeps no secret state at all. So it's essentially a public function. Based on just what I've told you so far, there's actually like a trivial way to satisfy this, right? Which is just to have each individual generate their own public key encryption key, and just send that to the key curator, and the key curator can just curate their keys by sort of adding them to a list. And in some sense, this is kind of like the trust model we want to achieve, but to make this sort of a interesting, non-trivial concept, for RBE, we require that the master public key is succinct, so it's independent of the number of users that join the system. Just to further explicitly compare these two, the central authority and key curator sort of both play the same role of producing this compressed public key. But the primary upside is that your key curator has no secret state, right? As I've said. But a slight downside, of course, is that they do require, when these are constructed, there will be some interaction that's required. So we define registered attribute-based encryption, which is essentially what you'd imagine it to be. It's the notion of registration-based encryption with the functionality of attribute-based encryption, right? So in traditional registration-based encryption, the users just send an identity to the key curator, but in registered attribute-based encryption, they register with a set of attributes instead. So in terms of our results, we have two constructions. The first one is we construct a registered ABE for an a priori bounded number of users from composite order bilinear groups, and this supports monotone Boolean formulas. And we also construct a unbounded registered ABE from obfuscation. For the purpose of this talk, I'll be primarily focusing on this first result, and just sort of just as sort of an overview of what we achieve, we compared to these prior works on just registration-based encryption, we sort of expand the functionality to be more ABE-like. And I'd also like to point out that our construction is more concretely efficient. So some of these prior RB constructions have ciphertexts that are in many terabytes in size. And the reason for this is that they rely on these non-black box techniques of either obfuscation or some sort of hash garbling, whereas we're able to sort of make black box use of crypto. Of course, there are some limitations to this construction. As I stated before, we can only support a bounded number of users. So at setup time, there needs to be, we need to specify how many users the key curator can curate into a single key. And in addition, we have to use a structured reference string rather than just uniform randomness. And finally, a slight downside in terms of practicality is that our CRS does grow quadratically with the number of users we need to support. Okay, so I'll try to go over our construction now. So first of all, as I said before, our construction uses composite order by linear groups. So if you aren't familiar with what this means, composite order, in our setting, we use groups which have a order which are the product of 3 primes. For the sake of this talk, I'll primarily just show what's going on in the G1 subgroup. The other 2 subgroups are mainly used for randomization for the sake of proving security. And of course, bilinear means that there's an efficiently publicly computable mapping, which is multiplicative in the exponent to some target group. Another sort of, simplification we'll make to the traditional notion of RB, of registration-based encryption, is that we show it's sufficient to only achieve this notion of slotted aggregation. So in traditional registration-based encryption, right, the key curator sees 1 key at a time, and sort of as the keys come in, they need to be able to incrementally update their master public key. But in the slotted version, rather than having to do this as things come in, the key curator can just look at all the keys, sort of save them up, and once all the slots have filled up, it just needs to produce this succinct master public key. And this turns out is sufficient to construct the full notion of registered attribute-based encryption using a standard powers of 2 trick. So our starting point is going to be the construction of just ABE in bilinear groups. And for simplicity, we'll only consider conjunction policies, though if this works for all monotone Boolean formulas just by replacing the additive secret sharing with like a linear secret sharing scheme. And so in these prior ABE schemes, you'll have a bunch of encryption group elements, and when you want to encrypt a message, what you do is you embed this message you pick this secret exponent s, you just blind the message by this one group element, and then you want to encode this secret s in a couple more places so that, at decryption time, you can actually recover this message. So how decryption works is that you'll notice we have this EGG to the alpha s, which is what we want to compute, and you pair your G to the S with this first decryption term, and you get the term you want, but you also have this additional blinding factor, right? So you'll notice that this blinding factor is also present in another part of the ciphertext. So you just pair this again, and this cancels out these 2 middle terms. And finally, you'll have this final term, which you also want to cancel out. And again, you could just pair this with G to the S, and if you have the attributes available, and then cancel out, and you can recover the message. So it turns out that for an ABE scheme, you can essentially make all of these group elements a public key, other than this one attribute group element for the attributes that you possess. So that's the ABE scheme, and now I'm going to give like a sort of high-level overview of how we get from ABE to registered ABE. So the first, so sort of as like a first intermediate, we construct a one-user registered ABE scheme, and the idea here is actually pretty simple. It's that we're going to take our ABE scheme and we're going to move essentially all the group elements and everything I described into the CRS of our registered ABE scheme. And so now all the key curator does is it just looks at the CRS and it says, you know, I'll like blind the message with these group elements only if the user doesn't actually have that attribute. And of course, the user still needs like a little bit of secret information, so we essentially give them the ability to have one additional attribute which they know the discrete log of, and so only they can decrypt only they can sort of deblind that part of the ciphertext. So once we have this one user registered ABE scheme, how do we move to multiple users, right? Well, the very simple thing to do is just, you know, multiply the keys, multiply all these, like make many copies of your one user scheme and sort of just multiply everything together. And, you know, this sort of this keeps your key curator as like this deterministic process, and you know, it makes everything compact. But of course, it's not quite that simple because you run into a little bit of some like correctness problems, right? So if you remember from a couple slides ago, how the ABE scheme works is you pair your ciphertext with this g to the t exponent, which is now in the CRS, and then this produces the message blinded by this additional group element term, right? And this group element term you can remove if you have the secret key using another pairing. But when you multiply these public keys together and you just encrypt normally, what you end up with is many of these like blinding noise terms. And it's not immediately obvious how you'd remove these other noise terms corresponding to other users' keys, right? Because, well, obviously, you shouldn't have other users' secret keys. But it turns out to fix this, what we can do is also just like blow up the CRS a bit more and produce a separate g to the t randomness for each user. So that way, when you do this pairing, you'll notice that the user 2's secret key is like u2 to the t2, but the terms that you have to actually deblind is this like u1 to the t2 and u3 to the t2. And it turns out that because when you can just give out these group elements when the indices don't match, and this doesn't harm security. And of course, these group elements, can be generated by the other parties and in the CRS, depending on which ones they are. And I just like to point out, I guess I'd just like to note that this is similar to some techniques used to construct vector commitments and batch arguments. So at this point, we're almost done. There's one last slight complication here is that, so we've solved this correctness issue, and we have an L user registered ABE scheme, but it only achieves a semi-honest security, as in if all the users do in fact register keys that were honestly generated, this would work, but security wouldn't hold for, you know, people just arbitrarily registering keys. And to fix this, we just require that the users attach a proof of well-formedness to their keys. In this group setting, this is pretty simple. In fact, it just requires like one additional group element. And from this, we can achieve malicious security, which is like the full notion of registered ABE security. So just to conclude, in our work, we define registered ABE, and we construct the first registered ABE schemes, one from bilinear groups, which is the one which I've been going over so far, as well as a general registered ABE circuit. General registered ABE from obfuscation. And I'd just like to point out that there have already actually been some interesting follow-ups on this work where some people have shown that our second construction of registered ABE for circuits sort of can readily generalize to registered functional encryption. And then one of these works also construct registered predicate encryption for inner product functionalities. And I'd like to also leave with some open questions. So, for ABE, maybe we could think about constructing registered ABE, like large universe registered ABE, or we can think about maybe is there a more generic approach to constructing a registered version of a primitive from the plain version. And finally, I'd just like to mention that we also have an upcoming work where we construct a both more asymptotically and concretely efficient bounded registered ABE scheme. And it's more efficient in that we're able to do this in prime order groups instead of composite. And the CRS size, rather than being quadratic, is nearly linear. Thank you.
So if there are questions, please come to the mic. Okay, if not, I have a very quick question. Okay. So you mentioned that your you have a structure reference string, and I wonder if this is because of the RSA modulus of the group, or if because of additional structure.
This is not RSA. This is any bilinear group, but the structure in the CRS comes from the fact that you need to compute these cross terms. So you need to compute you need to give out g to the x, g to the y, and g to the xy.
Okay. Thanks.
So I have a question of curiosity. So you pointed out that you've considered the threat scenario where users can be malicious. In the threat model where the curator can be malicious, for example, can modify the public master key in some way to get users to, let's say, leak information, is there a way for the users to, verify that the curator is behaving honestly or otherwise protect themselves from a dishonest curator?
Well, I guess that's sort of the point of this registered model where the curator is entirely deterministic. So if the users want, they could say okay, here's how did you get to this master public key, right? And so the curator should just be able to produce hey, here's all the people that registered, and then you can just verify that they indeed did generate everything correctly, and this doesn't compromise security because in RBE it doesn't matter, the curator's sort of internal state can all be public.
Okay, and just as a very quick follow-up question, because I think you probably already know the answer, but just in case. So in the scenario where the curator, let's say, maliciously excludes certain users' public keys and then presents to one user, let's say, the master public key version that excludes those public keys, that doesn't do anything that leaks confidentiality, does it?
Sorry, what do you mean by leaks confidentiality?
So the curator still wouldn't be able to do anything that would allow a different user to decrypt a message that they should not be able to decrypt.
Right. The curator only has access to public information, right?
Yeah, but
so they can't produce.
Yeah, but if the users can't, like, if the curator has access to more, as in, if the users don't know who all the users are, that sort of thing, or would they be able to verify who all the users are, or all their public keys?
Sorry, I don't quite know what you mean by that.
We could offline it,
Okay.
but
Okay.
yeah.
Let's thank the speaker again. So we have a 5 minutes break, and we'll start again at 11:40.